Okay, we now turn our attention to a prac called the Photometry of the Pleiades. This is a prac which is designed to introduce us to filters and their use in astronomy. So we're going to look at this star cluster here called the Pleiades. Now the Pleiades is a very special star cluster. They all formed out of the same galactic cloud at the same time, so they're all relatively the same age, and they're all relatively young because they're bright, hot and blue stars. There are thousands of these stars, and we here see only a very small select number of stars. But because they're all quite young, they're all main sequence stars. So that's the thing that we've got really to remember about these this little star cluster that we're going to be measuring. What we're going to measure about it, we're going to measure this star's brightness under two filters, the blue filter, and that's going to be called the MB. So I'll just get that bit better, knock that out. Okay, the MB, that's going to be the magnitude under the blue filter. Okay, good, it's finally working. And we're going to work MV, which is the magnitude, the apparent magnitude under the visual filter. Now the blue filter, as it says, is a blue filter that is placed upon the telescope, or these days it's electronically modified. Or we've got the visual filter here, which is a yellowish coloured filter. Remember, they can be a physical filter, or we can just modify the electronics to pretend to be filtering out certain photons. Right, once we've done that, we're going to go down to here and we're going to use this formula here. That formula is the distance modulus formula. We have it in two forms here, the one that is given to us on the formula sheet, and this is the actual one which we'll use, which is the rearrangement to get D over here as the subject, and we're going to be using that to find the distance to the stars in the cluster. Then we'll record all of our data down here in this table here. Okay, so here is where we'll record the visual magnitude, and here is where we're going to record the blue filter. Okay, now here's the program that we're going to use. So, just get that back to the. Okay, it's a simulation of a telescope, and I've just closed the dome so we can see it opening. And when it opens, we'll see the Pleiades cluster over here. I'll just get the thing. There's the Pleiades cluster, and tracking over here just tells us that we want I'll just turn it off so you can see as I speak. We want the telescope to track with the turn of the Earth, so therefore the stars don't move out of our view. By changing putting the tracking on, we can zoom really down to the photometry level. This means that we can actually this is the photometer here, and we can put it over top of these stars by moving it sideways. Just see if I can get that to move. Try and move it. Okay, moving it sideways. And we can get this star inside the photometer to take the reading. I've already set it up to take a baseline sky reading, which means that we can correct for looking and the seeing problems, which are the ground-based astronomy problems of selective absorption and light pollution. And the first coordinate, according to our book, the actual sheet, is this one here. So it's I'm going to type it in as 3 hours, 44:27, and the next one is 23:57:49, and we just say OK to that, and it moves it straight away to that star there. Right, we can take a reading now. Now the reading, we can change the filter from over here. There are 3 filters that this program allows us to have, and that would be the first one we want is the visual filter, the yellow filter. Okay, notice I've already taken a corrected mean sky, that's the sky pollution. Okay, and this is over here is the number of times it's going to take the reading. It's going to take 3 readings, and these readings will last for 10 seconds. And what it's going to count is it's going to count photons. So let's start the count, and as it comes in, we'll be able to see. So this is the star that it's counting, and our first reading is about to come in now, and it's calculated at 28 million photons. So what will happen in a few more moments is that the computer will take 28 million photons, it will average it with the next one, which is still 28 million photons down there. So it's approximately going to be 28 million photons. And that 28 million photons is going to be calculated into a visual magnitude. And the visual magnitude over here is 2.87. Okay, so we're going to now record that onto our sheet as 2.87. Okay, now we'll go and do the blue filter. So once again, we just change the filter, and this is the ultraviolet filter, which is not done in this prac, and here's the blue filter. We do it. Once again, it's going to start counting. Oh, sorry, I've changed the integrations, which is the number of times it counts, and we start the count. So we only have 3 counts, otherwise it takes forever. So this time, after it gets to 10, it's going to work out how many photons. There's 30 million. So there are 30 million photons coming through the blue filter, approximately. It's actually 31 million. Through the visual filter, we found that there was 28 million. That means there are more blue photons than, remember this is green and yellow. So there are more blue than green and yellow photons. That means that this star over here is a much hotter star, is a hot star, because a hot star puts out more blue than the rest. Okay, down here we can measure the magnitude for the visual magnitude for this filter. So putting it back over here, we had 2.87 before, that was 2.78. So all we need to do this is subtract them. The B minus V is called the colour index. Okay, and the colour index is a measure of the temperature of the star, and we use a following on the next page. We can use B minus V to work out the temperature. So subtracting these, this is 2.78 minus 2.87, and that equals negative 0.09. So just tidying that all up, that equals negative 0.09. Okay, I'm going to take a few moments and I'm going to record the same thing for the next 3 stars for us. So just I'll be back once those readings have been taken. Okay, I've now done the readings for the first 3 stars. As you can see, the last reading is just here. So let's put this onto our data up here on the final sheet. So this one here is going to be 3.88. This one over here is 3.81, and this one here was 8.373 and 8.669. So we're going to calculate the B minus V index for all of them now. So the first one was, it's always the B value, which is 3.81 in this first case, minus 3.88. So this is over here as negative 0.07. And the second one over here was, this clip, it's 8.669 minus 8.373. And this one here is, oh, that was a large value. Can I just check those values are right? Yes, it's 2.97. So 0.296. Okay, good, yeah. So we have values now for each of those. Now turning over the next sheet to this side over here, we're going to transfer most of these. I'm just going to copy those values down. So it's going to be, obviously we should have done the whole of this paper. We're only doing the top 3 stars here. Okay, so I've got those 3 values and I'm now going to the next sheet. So next question. Right, we're going to use this graph here now, and we're going to determine all these features about the star. Okay. Now we've got to remember that star A over here has a B minus V index of negative 0.09. This one is negative 0.07, and this one is 0.296. Okay, now we can determine its temperature and so on from the graph above, but in a few more moments, just before we do that, we're just going to have a look at these values. We know that a B minus V index goes from, if I can do that properly, how can I just get a better line than that? Okay, a B minus V goes from negative 0.5, okay, there's 0, and it goes up to 0.2, okay, or plus more than that. Right in the centre, 0 is a white star. The 0.2 are red stars, and these are blue. And this section here, we go from white through the colour gradations from white, yellow, yellow, orange, and so on to red. Okay. The 0 star is given as A0. So a perfect 0 star is going to be 0 as a colour index. So both of these stars here will be just on this side over here of the A. So it's just going to be over here. So the actual spectral class for these two over here will be probably more likely these ones here. This one and this one will be B stars. This, however, is all the way down this end, okay, and it most likely will be a K or an M class star. So we can just look at these values here that we get. This is the B minus V, and from the B minus V we can quickly determine the spectral class depending on the value. So let's have a look at the first ones, and let's go up and look at the temperature. So going up there we are. If I can get that to work perfectly in the right place, move that away. Okay, the first B minus V index was over here at, just gonna get this as pen, as negative 0.09. So it's negative, really we're looking at a number which is negative 0.1. Okay, so negative 0.1 is there. So going up to the temperature, crosses about there. So we're looking at here. So I reckon it's going to be 11, there's 12, so it'll be 11,700 approximately Kelvin. Okay, this is the surface temperature of that star. So the first thing is that for our first star, our B minus V was equal to negative 0.09, and our temperature, surface temperature, from this graph, which is 11,700 Kelvin. Okay. What is its absolute magnitude? Now the absolute magnitude is given by this line down here. Okay, these are commercially available graphs that are for main sequence stars, so you can just read them off. Going up here, there would be where we would use a different colour for this, and we read this way this time to about there. Okay, so I'm going to say that's approximately 0.7. So our absolute magnitude is 0.7. Okay, so you now can fill those values in on the diagram below. Okay, so going down one more time, let's navigate our way around this graph, this piece of paper. For star A, we can write in that the temperature was 11,700. Its spectral class we determined was probably a B9. Okay, its absolute value, actually that B8 could be B7 or B8 or B9. Its absolute magnitude was 0.7. Now its apparent magnitude is the visual magnitude. Apparent magnitude is equated as that, so it's negative 0.09, or you could just use negative 0.1. Okay. So I'm going to take a few moments and fill in the rest for us, so you can copy those values down. I'm going to check the spectral class to make sure that it is, which of these it is. I think it might probably would be a B7 if I look up on the diagram. Yes, it's probably B7. Okay. So give me a few moments and I'll be back once they are popped in. Okay, we've now completed the first two lines here. I've looked at this other apparent magnitude here. It's quite a large B minus, it's a large B minus V. So this is not apparent magnitude. This one was, it's in the wrong place, that one there. Just get rid of that. The apparent magnitude for the C thing here was 0.296. Now on our table, our graph, it only goes up to, we're going to do it together. So we're going to go up to, yeah. Okay. And 0.296, so we'll go to 0.3, so working with it together. So we can do this one. 0.3 would be here, so going up here, that's the first intercept, and there's the second intercept there. So going sideways, the temperature of this star would be approximately, that's 6,000, 7,000, 8,000, so we'll say 7,300 Kelvin. We'll classify that probably as an A9. Okay, because remember it goes A0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then F0, 1, 2, 3, 4, 5, and so on. The next one was the absolute magnitude. To go absolute magnitude, we use this one here, we go sideways. And I'll just use a little bit of a dotted line so I can help myself to get across. Going across, there is about it. Okay, so we'll be say 2.8. So 2.8 as the absolute magnitude, and obviously the apparent magnitude is equal to the visual magnitude, which was 8.373 from before. So that's how we get these three readings. I thought it was interesting to do that one because it was so much different than the others. Okay. Now we haven't got time to do all the others here. We'll just use these three values and move on. Okay, so let's go to the next part or the next question. You need these ones. Okay, we're going to use these values here. We only need to use two values. We need the second value that we discovered was these three values. This was the temperature. This one here was the spectral class. And this one here was the absolute magnitude. Now that's the important number there. This was the apparent magnitude. So remember that we can find the distance to a star using these two values. That's by the distance modulus formula. So we'll write down that the distance modulus formula is 10 times 10 to the little m minus big M on 5. Okay, so we can do these three here because we have these values here. For star A, the apparent magnitude, remember the apparent magnitude is now the visual magnitude, it's always the same, is equal to 2.87. We calculated that the absolute magnitude, there should be no capital, no bracket there, was equal to, going back, it was equal to 0.7. Okay, so we can now calculate the distance in parsecs using this formula. So popping it in, that equals 10 times 10 to the little m, take big M, so that's 2.87 minus 0.7 all over 5. Now that's got to be calculated first, and we just use it our calculator. So let's, I'll get the calculator up and I'll come back with a value for you. Okay, so let's type in the values. It's 10 times 10 to the, okay, and we're going to put this in a bracket, and this bracket is going to have a fraction in it. That's 2.87 minus 0.7. Okay, and on the bottom here, going down, is a 5, and close that bracket, and we say equals, so it's 26 parsecs. Okay, so the first value here, put in, where is the here, so this value here is 26.3, I think that was, parsecs. I can't really see it underneath all that there. Yeah, 23.30. Okay, you can now work out the next two values here using those. Okay, now after you've done that, we should get, remember this, it's all, these are all from the same cluster. So all of these stars are formed in the same gas cloud. Okay, it's quite a large gas cloud, so there's quite a significant diameter of this gas cloud. It's quite wide. Okay, so one star, this star over here could be 26.3. This one over here could be 100 parsecs away. But the average in the centre will be the average of all of these. Obviously, we should take, you know, there's hundreds and thousands of stars in this cluster, so we should take as many readings as possible to find how far the centre of this cluster is away from us. So could you now take time to calculate the other three values? They should be reasonably the same. Within, you know, maybe one would be 26, the other one might be 100, and so on. Okay, so take some time to do that now. Right, you've now calculated the other two values, but now we're going to ask to calculate how far it is away in light years, and we just need the conversion factor. So just say, for instance, we found that it was 26.3 parsecs away. Then if we multiply that by 3.26, we get the number of light years. So if we were to do 26.3 times 3.26, 26, that equals 85 light years. So, okay, and remember that was just done with this one here. You've got an average value for all of those three that you've done. If you did this in class, you would have had all 8 done, and then you could use that average and multiply it by 3.26, and you get the average diameter. Now, the average diameter would be the smallest value minus the largest value, because if the Earth is over here and we got one here at 26 parsecs away and this one is 100 parsecs away, then the diameter would be around about 74 parsecs. So you could use those values to work out the diameter of the cluster. Okay. I hope that helped you to get through this prac. You can now fill in the workbook, especially appreciating now that this process is finding the distance to stars using photometry, also known as spectroscopic parallax.